This is standard 8EE A4. We're going to use the scientific notation for several things. First, we're going to perform operations like addition, subtraction, multiplication, and division between numbers that are and are not in scientific notation. On this one, we're going to start with addition. And hold on. We've got 14.305, and we're going to add 9.57 times 10 to the second. Now, when we add, we have to have everything in the same scientific notation. Everything would either have to be 10 to the second or set up like this without scientific notation. So first we need to convert one of these. And I've decided I'm going to convert this one to 10 to the second. Now, think about it. 14.305 is the same as times 10 to the 0, because 10 to the 0 is 1. So 14.305 times 10 to the 1 is still itself. What we need to do is convert it to something times 10 to the second, and we need to know how to do that. The way we do that is to use LARS. Our statement LARS means left, we get add, we go right, we subtract. So if we're going from 0 to 2, we're adding 2. So 0 to 2, if we add 2, let's think about that, guys. Then if we're adding 2, we need to go left 2 spots. 1, 2. That's 0.14305 times 10 to the second. So let's substitute that right here in for this number. 0.14305 times 10 to the second plus 9.57 times 10 to the second. If I add those, I have 9.71305 times 10 to the second. Move that 2 places, and that's 971.305. What if you subtract? Same thing occurs. If you subtract, you have to have the same exponents here. So if I'm subtracting, I need to convert one of these. In this case, I'm going to convert 2.1 times 10 to the negative 6 to something times 10 to the negative 5th. Well, if I go on the exponents from negative 6 to negative 5, I've added 1. LARS says if you add, you go left 1 spot. So I need to move left 1 spot. That would be 0.21 times 10 to the negative 5th. Here's what we've got. 3.5 times 10 to the negative 5th minus 0.21 times 10 to the negative 5th. If you subtract those, see how your exponents are the same here? You've got 3.29 times 10 to the negative 5th. What if we multiply? A bead weighs 3.7 times 10 to the negative 2. If you need to ship 7,000 beads of the same weight, what would be the total weight of the beads to be shipped? We need to multiply 3.7 times 10 to the second. And I've set it up right here. Multiply that times 7,000. Well, you can either multiply the 7,000 times 3.7, or you can convert the 7,000 into scientific notation. I've converted it. 7,000. I would move it 1, 2, 3 places to get to 7. So that's 7 times 10 to the 3. When I have a positive exponent, represents a number that's bigger than 1. So we know this exponent's bigger than 1. Now, let's substitute this in. We had 3.7 times 10 to the negative 2. And we've substituted that in there. Okay, my pencil will work. We've substituted this, we put this in, then we've substituted 7 times 10 to the 3 in place of the 7,000. Let's collect our terms that are alike here. 3.7 and 7 are just numbers, where these are 10s with exponents. 3.7 times 7, 10 to the negative 2 times 10 to the third. If I multiply 3.7 times 7, I get 25.9. So let's substitute that in place of this. If I've got 10 to the negative 2 times 10 to the third, I've got 10 to the negative 2 plus 3. Add those together and you've got 10 to the first power. That's 25.9 times 10 to the first power. Move it 1 place, and that's 259. Your package would weigh 259 grams. Now, how about if you're dividing? Let's look at a division example here. If I've got 3.5 times 10 to the 5th and divide it by 0.067, I could either divide the 3.35 by the 0.067, or I can convert this to scientific notation. I'm going to convert it. If I convert this, move it 2 places, I have 6.7 times 10 to the negative 2. It's a negative because this number is less than 1. I can substitute it in 3.35 times 10 to the 5th divided by 6.7 times 10 to the negative 2. Now, let's divide these two. 3.35 divided by 6.7 gives me 0.5. 10 to the 5th divided by 10 to the negative 2. Whenever I'm dividing that, I've got the same basis, so I need to subtract my exponents. 5 minus a negative 2. 5 minus a negative 2 is 5 plus 2, which is 7. 0.5 times 10 to the 7th. That's 5 million. Because if you move this 7 places, you would wind up with 1, 2, 3, 4, 5, 6, 7, 5 million. Another part to this, you can use scientific notation to choose appropriately sized units for very large or very small quantities. Think of this. A line is about 1.39 times 10 to the negative 5th meters. See, that's going to be much smaller than a meter. The negative 5th means it's much smaller. In fact, you would wind up moving this 5 places. 1, 2, 3, 4, 5. You're talking about something that is 0.0000139 meters. Which of the following would be a better unit for expressing this? Millimeters, which is very small. That's 1,000th of a meter, right? Miles, yards, or feet. Well, if this is very small here, millimeters would be our best option. And then interpret scientific notation generated by technology. Let's look at these. These are calculator outputs. We want to write them in scientific notation. This E means times 10 to the. So this simply means 2.45 times 10 to the, and see positive 23, that's a positive 23 value. How about this one? 3.5, and that E means times 10 to the. And here we've got a negative 4.